Yeah, so today we begin with the first chapter, and as it always happens when we start a mathematical theory, we begin with a parade of definitions and a whole bunch of basic theorems, which we need to set. That's a stage setup for what's to follow. So, deep and non trivial results will keep coming later. In this chapter, we shall mainly see lots of examples. And the notorious example that we shall see is the dihedral group of order 10. We are trying to find the representations of these dihedral groups of order 10, and that will involve some work because we are not using any theory. We are trying to do it from scratch. So let's begin with the basic definitions, and let me begin by sharing my screen. Can you see my screen?
Yes.
Okay, so the so we shall introduce the most basic notions connected with the idea of representations, such as irreducibility, indecomposability, complete reducibility, and mash case theorem, unit equivalence of representations, and and so on, and a parliament of irreducibles, for instance. We'll see lots of examples. So the basic definition is, of course, the definition of a representation. A representation of a finite group G is a group homomorphism rho from G to GLV, where V is a vector space. We shall assume that the dimension of the vector space is positive. So V is not the zero-dimensional space. Later on, when we discuss the ring of representations, we will have to allow the dimension to be zero, but that will come in chapter 7 or so. Until chapter 7, the dimension of the vector space will always be positive, and we shall usually assume that it is finite dimensional, and the dimension of V is called the degree of the representation. Now, if rho is a group homomorphism, then the value of rho at G, so rho G, will sometimes be denoted by rho sub G. This is very common because we want to think of rho G as a linear transformation from V to V. So the G has been sent downstairs as a subscript, so that I can put I can use the rho sub G as a function from V to V. The most obvious example, of course, is the trivial representation where everything goes to the identity operator. So G rho sends every little G to the identity map from V to V. In case the dimension of the vector space is 1, that is, the vector space is the complex field, the representation rho is then a group homomorphism from G to C star, in case dimension of V is 1. Because GL1 C is simply C star. And in particular, one has the trivial representation of degree 1. That is, this is called the trivial representation of degree 1. Remember that the degree of the representation is just the dimension of V. Okay, so we certainly have an example. So all vector spaces in this course will be over the complex field. Occasionally, very rarely, we'll be looking at the real field, and that's about it. We shall never be looking at finite fields and fields of characteristic P and such in this course. So some trivial examples. Take the cyclic group of order 2. It has two elements, and there are two group homomorphisms from the group to C star. Namely, it has to map into plus minus 1, and there are two such group homomorphisms, the trivial one and the isomorphism, which sends the generator to the generator minus 1. And then the cyclic group of order 4. Now the cyclic group of order 4 has two generators, I and minus I, and I can send the generator I to any of the four possibilities, plus minus 1, plus minus I, and I have four options for a mapping from G to C star. And the first exercise is to list all four degree 1 representations. So here I'm only looking at degree 1 representations first, and take a cyclic group of order n, and then you send the equivalence class, the residue class of m, you send it to x of 2 pi I m by n. That defines a representation of degree 1. You can list all the other representations of degree 1. Now we come to an interesting example of representations of degree 2. Take the equilateral triangle. The vertices of the equilateral triangle are 1 omega and omega squared. And omega is the cube root of unity, 2 pi I by 3, x of 2 pi I by 3. Complex conjugation will take omega to omega squared and omega squared back to omega. It fixes 1. And so that is certainly, a complex conjugation certainly fixes the equilateral triangle as a geometrical object, but flips the vertice, flips these two vertices. And the complex conjugation is as described this 2 by 2 matrix 1 0 0 minus 1. And then I can rotate the plane by fixing the origin through angle 2 pi I by 3. And the rotation matrices are tau and tau squared. Tau squared will be rotation through angle 240 degrees. And so these matrices tau and tau squared have been displayed here. And tau cube is obviously 1. Sigma squared is obviously 1. Tau sigma tau is tau squared sigma. And tau sigma tau is sigma, and so on. And so if you keep computing sigma tau sigma etc., you will keep getting again and again these 6 elements: 1 sigma tau, tau squared, sigma tau, and tau sigma. So this is a group of order 6, and it's evidently a non-abelian group of order 6 because tau sigma and sigma tau are distinct. And so there is only one non-abelian group of order 6, the symmetric group on 3 letters. And so we have realized the symmetric group on 3 letters as a subgroup of GL2R, and hence as a subgroup of GL2C. So this provides us a degree 2 representation of the symmetric group S3. Of course, S3 has two other representations. I can take all the elements of S3 and map it to C star, then namely map it to number 1 sitting inside C star, or I could take a permutation and I can map it to the sign of the permutation. So you got the trivial representation of degree 1, the sign representation, which is also degree 1, and this degree 2 representation. Later we are going to see that these 3 representations are what are called as irreducible representations. And there are only 3 irreducible representations of S3. The next is a generalization of S3, the dihedral group. The dihedral group is a group of symmetries of a regular n-gon. So take the vertices of the regular n-sided polygon as the nth roots of unity. Omega is exponential of 2 pi I by n. And then as we did here of 120 degrees rotation, here we shall do a rotation through angle 2 pi by n, and a reflection which fixes 1 and which will take omega to its complex conjugate. And the complex conjugation is denoted here by letter T, the matrix 1 0 0 minus 1, and the rotation capital R is rotation through angle 2 pi by n. And so now we got, just as in the case of the equilateral triangle, we had 6 elements. Here I'm going to get 2n elements. T squared is identity. Then I have the rotation, and then you can keep rotating it. You can keep iterating this rotation, and I'll get all the rotations. I r squared da, 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 r to the power n minus 1, and all these rotations can be left multiplied with t, and I'll get n more elements. And then what happens is that if you take RT will be TR to the power minus 1. So that's easy to check, and I given the equations here. And so we got a non-abelian group of order 2n. This is the group of symmetries of a regular polygon with n sides. This is called the dihedral group of order 2n. The dihedral group of order 2n has been realized as a subgroup of GL2R, and so it's a subgroup of GL2C. All right. Now let us go to the next one, a two-dimensional representation of the symmetric group S4. Let us take A to be omega 0 minus omega squared 1 and B to be 1 omega squared 0 omega. Right? And so I have two matrices A and B, and omega is a cube root of minus 1. And these A and B, and one can check one can calculate a squared, a cube, etc., b squared. I can keep multiplying a b, and so on and so forth. And I can, in short, I can create words in a and b, and these matrices have finite order, and I will generate 24 elements. That's an exercise to generate 24 elements, and these 24 elements form a group, and this is a group, the symmetric group on 4 letters, the symmetric group on 4 letters, group of order 24. And here I've got automatically a two-dimensional representation, a degree 2 representation of S4, the group of permutations on 4 letters. Of course, you may ask, how did I get these two matrices? How did I get these two matrices? Well, there are two answers to that. I just picked it up from a book of Taylor and Lehrer on page 10. But Taylor and Lehrer explain that this can be obtained through a systematic algorithm called the Shepard-Todd algorithm. For us, the Shepard-Todd algorithm at this stage is not important. What is important now is that we have here a explicit degree 2 representation. Okay. And again, for the symmetric group S4, we got the trivial degree 1 representation where everything goes to the number 1 in C star, and the sign of a permutation. That also gives you another degree 1 representation. We got a degree 2 representation. We are also going to get other representations of degree 3, but we'll wait for some time before we see the degree 3 representation. And I've been talking about the sign of a permutation. For Sn, the permutation group of permutations on n letters, we got the map G to C star given by a permutation G goes to the sign of G. That's a sign representation. It's a degree 1 representation. So as I explained, S3, we got 3 representations, and by a remarkable coincidence, S3 also has 3 conjugacy classes. And the fact that these two numbers, 3, match, that there are 3 conjugacy classes and there are 3 so-called irreducible representations, is not a coincidence. It's going to be a part of a general theorem. Then, when we talk about any part of mathematics, we talk about equivalence. When we talk in topology, we are looking at concepts which are invariant under, say, homeomorphisms. So, homeomorphism is some kind of an equivalence in the category of topological spaces. If we have got two spaces which are homeomorphic, if one of them is compact, so is the other. If one of them is connected, so is the other. So here, what is the corresponding notion of equivalence? Here, the notion of equivalence, when are two representations said to be equivalent? Two representations are said to be equivalent, phi and psi. So phi. So first, let us look at representations. Let us take the vector space to be Cn. So we got two representations, phi and psi, from G to GL and C. The vector space is Cn, and so the invertible linear transformations from Cn to Cn are denoted by GL and C. They are said to be equivalent if there is an isomorphism of the vector spaces Cn to Cn, which such that all the matrices phi G and all the matrices and the corresponding matrices psi G are simultaneously conjugated by this T. There is a single T which conjugates each phi G to psi G. And then we write this as phi wiggles psi. There's a common linear transformation T which conjugates all of them. More generally, instead of GL and C, one can work with GLV, where dimension of V is n, and I can take a representation phi, which is a map, which is a group homomorphism from G to GLV, and a representation psi, a group homomorphism from G to GLW. And then we say that phi and psi are said to be equivalent if there's an isomorphism, T from V to W, such that the phi G's and the psi G's are conjugated by T simultaneously for all G's. Is the definition clear to you?
Yes.
Now, A simple example of equivalences, I could take the cyclic group of order n, and I have the I have the representation that I have given you already. It takes the residue class of m to cos 2 pi m by n minus sine 2 pi m by n sine 2 pi m by n cos 2 pi m by n. Another one, psi, it takes the residue class m to x of 2 pi I m by n 0 x of minus 2 pi I m by n. These are both representations of the same group, the cyclic group of order n, show that phi and psi are equivalent. If you have to produce a linear transformation from C2 to C2, which conjugates phi, which conjugates all these matrices, these two matrices simultaneously as m runs from 0 to n minus. And this matrix, here is a hint, try this matrix I minus I 1 1. The map T in the above definition is called an intertwiner or an intertwining map. Okay, we shall generalize the notion of intertwining map later, even when the representations are non-equivalent. If the representations are not equivalent, then how do I do it? I just say that phi psi g composed with t equal to t composed with phi g. That is that this diagram must commute. That would be the definition of an intertwiner actually. When t is not a isomorphism. Okay, the standard representation of Sn. This is a very important concept. Later on, we are going to see another notion called the regular representation. The standard representation and the regular representation are very different. One must take care not to confuse the two. It's common at the beginning to get confused between the two, but right away I'm pointing out that these are different. The standard representation. Well, how do I get the standard representation? So we start with the identity matrix, n rows and n columns. Take a permutation in Sn and simply apply that permutation to the columns of the matrix. And what I get, and the matrix so obtained is called A sub sigma. Sigma going to A sub sigma. That is a group homomorphism from Sn to GLNC. And a permutation matrix is evidently a non-singular matrix, and that's a group homomorphism. And this group homomorphism is a representation of degree n, because the vector space is Cn, and so it's a degree n representation. This is called the standard representation, and the matrices are called permutation matrices. Now, the sum of the entries in a permutation matrix, one must appear exactly once in each row and in each column. So the row sum must be 0, and the row sum must be 1, and the column sum must be 1. In other words, all these matrices A sigma have a common eigenvector 1 1 1 1 1 transpose. This common eigenvector V. So that is, if phi from Sn to GLNC is a standard representation, then phi g of V will be equal to V. Phi g of CV will be equal to CV for all Cns. And so we say that the one-dimensional subspace spanned by V is G invariant. So now let us formally define what is a G invariant subspace. So let us take a representation rho from G to GLV, and a vector subspace W is said to be G invariant if for each little g in capital G, the linear transformation rho sub G. Remember, rho sub G is the value of rho at G. The value of rho at G is an element of GLV. It's a linear transformation from V to V, and W is a subspace of V. So rho sub G of W must be contained in W, or rho G. Okay, rho sub G is the same as rho G. Rho G is a linear transformation that has W is invariant under rho G, and this must happen for all G's simultaneously. That is, this W must be invariant under rho G for all G. That's a pretty strong condition. That's a very, very strong condition. If the group is large, then expecting this W to be simultaneously invariant under all the rho g's is quite a stringent condition. Obviously, uh, obviously, for any representation, we have two examples of G invariant subspaces. The zero subspace is obviously G invariant, and the whole space V is obviously G invariant. These are the trivial G invariant subspaces. A representation a representation rho from G to GLV is said to be irreducible if the only invariant subspaces are the trivial ones. That is, other than 0 and capital V, there are no other invariant subspaces. So, immediately, the standard representation of Sn is not irreducible because we have a non-trivial G invariant subspace, namely the linear span of the column vector 1 1 1 1 1 1 1 1. Is this point clear? Any questions? Can I take up any questions?
It's clear, sir.
Now, suppose I take a one dimension, a degree 1 representation. If I take a representation of degree 1, that is, if I take a group homomorphism from G to C star, that means that GL1C. What's a vector space? C. What is the dimension? 1. What are the proper are there any proper subspaces at all? There are none. The subspace is either 0 or the whole thing. And so it is obviously a irreducible. So any degree 1 representation is automatically irreducible. What about degree 2 representations? When will a degree 2 representation be irreducible? If it is not irreducible, we say it is reducible. So theorem 1.1, a degree 2 representation rho from G to GLV is said to be reducible if all the rho G's have a common eigenvector. Of course, if all the rho G's have a common eigenvector, then it is obviously reducible because the eigen subspace is G invariant. It's a one-dimensional G invariant subspace, and one-dimensional, so it's a proper subspace. Conversely, suppose it is reducible, that means there exists a G invariant subspace W, which is proper. That means that it is not 0 and it is not the whole thing. And since the dimension of V is 2, dimension of W must be 1. And so W must be the C linear span of some non-zero vector V naught. And rho G of W is contained in W will mean rho G of V naught must be lambda V naught for some lambda. And so all the rho G's have a common eigenvector V naught. Right? They all have a common eigenvector V naught. That does it. Next, so let us go back to the example. Let us take the degree 2 representation. S3 has our favorite example. S3 is the group of symmetries of the equilateral triangle. The vertices are 1 omega omega squared, and the first matrix here is a complex conjugation, and the second matrix is rotation by 120 degrees. The question is that there's a degree 2 representation. So for a degree 2 representation, to understand whether it is irreducible or reducible, I just want to find out whether the matrices have a common eigenvector or not. We can immediately see that these two matrices do not have a common eigenvector. Why? Because what are the eigenvectors of the first one? E1, E1 cap, E2 cap. Neither E1 cap nor E2 cap is an eigenvector for the second one. So that's it. These matrices do not have a common eigenvector. Therefore, this representation is irreducible. So for S3, we have three irreducible representations: two degree 1 representations and one degree 2 representations. Again, the number of irreducible representations is exactly 3, and it matches with the number of conjugacy classes. This is one of the theorems that's going to come in the second chapter. Now, suppose I take a degree 3 representation. Rho from G to GLV is a degree 3 representation. Then rho is reducible if and only if all the matrices, that is, all the rho G's, all these linear transformations have a common eigenvector. So what we have proved in the theorem? We have proved the theorem for two degree 2 representations. The exercise is try to prove the same thing for degree 3 representations. At this juncture, it's a little messy to do it. and but it will become very clear and very transparent once we prove a couple of theorems. Okay, this result is going to fail for degree 4 representations because a degree 4 representation can break up into two degree 2 representation, or come up with an example to show that that for degree 4 representations it is not true that if all the matrices rho g have a common okay, it's not true that it is reducible if and only if all of them have a common eigen. In one direction it's true, in the other direction it is false. The next theorem is, why is it that for abelian groups, the cyclic group of order 2, cyclic group of order 4, cyclic group of order n, we have only been looking at maps into C star? Why did we not look at maps? Why did we not look at degree 2 representation, degree 3 representation? There is a reason for it. All irreducible representations of a finite abelian group are one dimensional. Let us take a representation rule where G is a finite abelian group. The let us look at the linear transformations rho G, where G varies over G. This family of linear transformations is a commuting family. A commuting family of linear transformations have a common eigenvector. Remember, we are working over the field of complex numbers. We are working over a field of complex numbers. It's extremely important that here the field is a field of complex numbers. All these linear transformations have a common eigenvector. If you work with the field of real numbers, there may not be any eigenvector because there may not be any eigenvalue. Here, because the base field is complex, we have this. This is true. That the linear transformation. So it's a commuting family. They have a common eigenvector V naught, and therefore the eigen subspace will be fixed by all these operators simultaneously. Now let us take the dihedral group. The dihedral group is already a subgroup of Gl2C. And again, we can see that T and R do not have a common eigenvector. Again, the degree 2 representations. So, if they have a common, if all the matrices have a common eigenvector, then it is reducible. Otherwise, it is not reducible, it is irreducible. So, this is an example of a irreducible representation for the dihedral group. Now we'll look at one particular concept which is significant only for non-compact groups, the notion of indecomposability and irreducibility. A representation is said to be decomposable if there are G invariant subspaces V1 and V2 such that V1 and V2 are both proper subspaces, that is, they are both non-zero and neither of them is the whole space V, and V is V1 direct sum V2. So there are several things we need. We need two vector subspaces V1 and V2. Both of them should be proper. V should be a direct sum of V1 and V2. V1 and V2 must both be G invariant. Lot of things. Now, why are we calling it decomposable? Because now what happens is that rho G is a linear transformation from V to V. We can restrict the linear transformation to linear transformation to V1 or V2, and then we can get a sub representation. So rho G restricted to V1 will map V1 to V1. Rho G restricted to V2 will map V2 to V2. So you will get a representation on V1 and a representation on V2. Correct? And or for example, I can take a basis for V1 and I can take a basis for V2 and I can string them together and get a basis for V. Correct? Now, what will be the matrix of rho G with respect to this basis? It will be a block diagonal matrix. No, it will be one block. Suppose dimension of V1 is K and the dimension of V2 is L. Then the matrix rho G will have a K by K block, 0, 0 and L by L block. So it's like taking two individual representations on V1 and V2 and just stringing them together. Okay, that's why it's called decompose. So I decompose the representation rho into two sub representations, one on V1 and one on V2. Like a block diagonal matrix, a K by K block and an L by L block. K plus L is the dimension of V. So I decompose the representation. So of course, by very definition, decomposable implies reducible because I have a non-trivial G invariant subspace. Or by contraposition, rho irreducible implies rho indecomposable. The converse is not true. This way, the opposite implication will fail. Rho indecomposable will not imply rho is irreducible. Rho indecomposable will not imply rho is irreducible. For finite groups, the converse is true. For compact groups, the converse is true. So the two notions are identical for compact groups and in particular for finite groups. We don't have to worry about it. We have to worry about it only when we work with non-compact groups. Unfortunately, non-compact groups are going to be extremely important in many parts of mathematical physics, and so we can't and so this distinction will become very, very significant. Yes, sure. So let us look at the simplest example of a non-compact group, an infinite cyclic group, Z. So non-compact group. And let us take a representation phi from G to GL2C. Phi of n, because any degree 1 representation is already irreducible. So the smallest degree will be 2. And we take this degree 2 representation 1 and 0, 1. Now, E1 cap is a common eigenvector for all these matrices. So the the linear span of E1 cap is a G invariant subspace. Question is, will this representation decompose? If there are two invariant subspaces complementary, then they must have one. Then it must be V1 direct sum V2. V1 will be one dimensional. V2 will be one dimensional. Because V1 is one dimensional, any non-zero vector will be a common eigenvector of all of them. Take any non-zero eigenvector V2, that will be a common eigenvector for all of them. So it will follow that all these matrices have a common the basis of eigenvectors. All the matrices have two linearly independent eigenvectors common to all of them. That's blatantly false. Correct? Yes?
Yes, sir.
Is this clear? Completely false. And so we are given this is just a cautionary note. We don't have to worry about this distinction for a large part of this course. Okay. So now we come to next business. Irreducibility and indecomposability are intrinsic notions. Suppose if phi and psi are representations from G to GLV and G to GLW, and they're equivalent representations. Suppose you got two equivalent representations, then both are decomposable or both are indecomposable. Both are irreducible or both are reducible. So reducibility and decomposability, they are intrinsic notions. They do not depend on they're equivalent. That is, they're preserved under equivalence. So take the isomorphism which intertwines the two representations. Okay, suppose psi is not irreducible. That means there is a G invariant subspace, non-trivial G invariant subspace W naught. So T inverse of W naught, call it V naught, that is also going to be non-trivial invariant subspace. It will be non-trivial because T is an isomorphism, and it will be G invariant because of the intertwining property. That's all. And so phi is also not irreducible. So psi reducible implies phi reducible, and the case of decomposability is very similar. Unitary representations. Now, a representation means what? A representation is a mapping, is a group homomorphism from G to GLV. The GLV, now we are going to work with a complex vector space. Okay, and we are going to work with a complex vector space endowed with a Hermitian form. Once a complex vector space is endowed with a Hermitian form, GLV has a very nice subgroup. What is that subgroup of GLV, which is very distinguished thanks to the existence of a Hermitian form? The unitary group. So we say that phi is a unitary representation if each phi g is a unitary operator with respect to the Hermitian form. That is, each of these, if you think of in terms of matrices, each of these matrices phi g must be a unitary matrix. That means it preserves the Hermitian form. That means the Hermitian form phi g v1 product with phi g v2 is the same as v1 v2 for all v1 v2 and for all g. That means simultaneously all of them should be the Hermitian form must be simultaneously preserved by all these operators phi g. A 1 cross 1 unitary matrix is simply a unit complex number. And so, degree 1 unitary representation is simply a group homomorphism from G to T, the circle group. The circle group which we encountered in chapter number 0. So, let us take some simple examples. The group of the real numbers. We've got a beautiful example of a unitary representation. Phi of x equal to e to the power 2 pi I x. That's a unitary representation of R. We will see many other examples of unitary representation. Let us take a unitary representation phi from G to GLB, where G is any group. Unitary representation, okay? I'm already telling you that the representation is unitary. The group is any group. I'm not saying it's compact, non-compact, finite, infinite, nothing. I'm not saying anything about the group. Then phi is either irreducible or decomposable. That is the decomposability and irreducibility. That problem, the problem disappears. If you for unitary group, for unitary representations. I should say phi is either irreducible or reducible. But now I'm saying that phi is either irreducible or decomposable. You know that decomposable implies reducibility. Okay, other way around. Okay, this is clear. So for unitary representation, irreducibility and indecomposability are one of the same notions. Suppose phi is not irreducible. Okay, that means that there is a vector subspace V naught, which is a proper subspace, not the zero subspace, not the whole thing, and which is G invariant. The fact that V naught is G invariant means what? Take the operator phi g. Phi g is a unitary operator. Point number one. Point number two is that V naught maps to V naught under phi g. Now remember, when you have a unitary operator, more generally, when you have a complex vector space V is a complex vector space endowed with a Hermitian form. And have a linear transformation from V to V. So, and I have a subspace W. And that subspace is invariant under the linear transformation. The linear transformation maps the subspace into itself. Then what is the next thing you're going to ask? Yes? You're going to ask whether the orthocomplement is also going to be invariant, right?
Yes, sir.
When will that happen? That will happen if the operator is Hermitian, normal, in particular unitary. That is the, but we are not interested in Hermitian operators. We are not interested in normal operators because, in general, because these operators are supposed to form a group. So the natural thing to look at will be the unitary operators. So the important thing is that if it is, since the phi g is a unitary operator and the V naught is getting fixed, the ortho complement is also going to get fixed. And this is going to happen for all the G's. the V naught is going to be fixed by all the phi g's simultaneously. So V naught perp is going to be fixed by all the phi g's simultaneously. And so V naught perp is also going to be G invariant. So V naught is G invariant, V naught perp is G invariant, V is a direct sum of V naught and V naught perp, and it is decomposable. You're finished. Right?
Yes, sir.
That's all that there is to it in this. So what I have described in these notes is I have actually checked. Of course, I made a general remark that if you have a linear transformation, if you have a unitary operator which fixes V naught, which is invariant, if V naught is invariant under a linear transformation, then V naught perp is also invariant under the same linear transformation, and I have verified it in the next 3 lines. So this verification is a part of a general theorem in linear algebra courses, that if you have an operator which is unitary, normal, self-adjoint, and if a vector space V naught is invariant, then the ortho complement is also invariant. Now we shall show that for finite groups, and later we shall show for compact groups, every representation is equal to unitary one. Since decomposability, reducibility are preserved under equivalence, now I am saying that every representation is equivalent to a unitary representation. And for unitary representations, reducibility and decomposability are one and the same. Therefore, they are one and the same for all representations, provided the group is finite or compact. Because only for these two groups, the finite groups and compact groups, are we going to show that every representation is equivalent to a unitary representation. The idea is very simple, namely averaging. So take a representation rho from G to GLV, any representation of a finite group, and V is finite dimensional. Now we want to show there is a Hermitian product. There is a Hermitian product on V with respect to which all the linear transformations phi G are simultaneously unitary. In other words, there is a G invariant Hermitian form. That means the product of phi GV and phi GW is the same as the product of V and W. How do you cook up this kind of a Hermitian product? Very easy. You take any favorite Hermitian product, Hermitian form, fix a basis and work with it if you like. Take a or work with Cn to begin with, whatever it is. You can take a fixed Hermitian form on the vector space V, double brackets. Now you do averaging. You take summation over G, phi GV, phi GW with respect to this chosen inner product, and you divide by the number of elements in the group. 1.3 is an averaging. In other words, you took any Hermitian form and you averaged it over the group. Now you have to check that this is again a Hermitian form. The fact that it is again Hermitian is completely routine. It's absolutely routine matter. And I will leave it. Now we have to check that this does the job of invariance. This has the invariance property. The only non-trivial thing is to check that it has invariance property. That I take an element, arbitrary element H in the group, phi HV, phi HW. What is that equal to? 1 upon G. The 1 upon G I brought it to the left hand side just for notational convenience. Summation over G, the chosen in the product, phi G, phi HV, phi G, phi HW. But phi is a group homomorphism. So this is phi of GH, here also phi of GH. But as G varies over the group, GH will also vary over the group. So this is a dummy. So we're changing the dummy variable from GH to G. I can see that again, and I just have to bring the mod G on the right hand side, and then I'll get that it is again single bracket VW. So we have checked that this 1.3, the left that this definition 1.3 does indeed give me a G invariant in a Hermitian form. The finiteness of the group was used mainly to do the averaging. For a compact group, we have a Haar measure that's available, and one can use the Haar measure to do the averaging. The summation will become an integral. The details will come in a later chapter. Complete reducibility. A representation rho from G to GLV is said to be completely reducible if I can just break this V into a direct sum V1 direct sum, V2 direct sum, Vk, where each Vj is G invariant, and the representation and the representation induced on them, rho j, the restrictions, rho j from G to GL Vj obtained by restricting rho g to Vj is irreducible. That means I have broken it into atoms. So irreducible representations are like atoms, and a complex representation can be broken up into simpler into its atomic pieces. So that is the idea. Again, complete reducibility is preserved under equivalence. If you have two equivalent representations and if one of them is completely reducible, then the other one is also completely reducible. Now we have to prove a theorem, the first major theorem in this course, Maschke's theorem. Every representation of a finite group is completely reducible. Well, since complete reducibility is preserved under equivalence, we may assume without loss of generality that our representation is a unitary representation. So let phi from G to GLV be a representation of a finite group. If dimension of V is 1, the job is done because a one-dimensional representation is already irreducible and there's nothing further to be done. The general case proceeds by induction on the dimension. Assume that the dimension of the vector space is n and that the theorem is true for all representations of degrees strictly less than or equal to n minus strictly less than n. So now take a representation from G to GLV. Now the previous theorem says that phi is irreducible or decomposable. If phi is irreducible, job is done, or phi decomposes. So in other words, there are two subspaces V1 and V2, both proper, and V is a direct sum of V1 and V2, and V1 and V2 are both G invariant. So I can restrict the representation phi to V1, that is phi G can be restricted to V1. You get a representation phi 1. Phi G can be restricted to V2. I get a representation phi 2. And these are again these two representations have strictly smaller degree, and so they will each break up into its atomic pieces, namely irreducible pieces, and put them together, and the job is done. Now the proof only relies on the previous theorem that if you have a unitary representation, then every G invariant subspace has a complement. That is the only thing that we used. That's the only thing that we used. So that theorem will be true even for compact groups. As I said, if you have something which breaks off into pieces, V1 direct sum, V2 direct sum, Vk, where each Vj is G invariant, take a basis of Vj and string them together to get a basis of V, and the matrices phi and the matrices with respect to the basis will be block diagonal matrix. So, so that's the idea. So let us return to the exercise posed earlier. Suppose you got a degree 3 representation. Then rho is reducible if and only if all the rho g's have a common eigenvector. Okay. Well, there is a proper G invariant subspace, call it V1. If dimension of V1 is 1, then take a non-zero vector in V1 and there will be a common eigenvector for all of them. Otherwise, by Maschke's theorem, we know that V will be V1 direct sum V2. If dimension of V1 is not 1, then the dimension of V1 must be 2. Then dimension of V2 must be 1. Pick a non-zero vector in V2 and we have common eigenvector. So the theorem is also true for degree 3 representation. It is not true for degree 4 representations. And now some general exercises on linear algebra that we don't need for a long time. A commuting family of unitary operators have a common eigenvector. I think we stop it here and we'll continue this next time.